This video is an extra optional help video to help you with combustion analysis or using formulas as elemental analysis. So if you're watching this, that probably means that you had difficulty with the combustion analysis question in the topic 5 lecture for part 2. Maybe not, maybe you're just here for extra support, but if you need help, the first thing I am going to do is talk you through that question that was from that lecture, and then I have a few more examples that we will go through together. So let me add a page here so that I have enough space for this, and let's go through the one from the topic 5 video first. All right, so remember that in combustion analysis, you are going to be finding the carbon that was in your original sample of your compound from the carbon dioxide. You're going to be finding the hydrogen from the water that was produced, and then you'll need to be finding the oxygen or any other element, if there is one, from the difference between those two masses and the mass of the initial compound. So you're on the lookout for definitely all kinds of different information here. So the first thing, if you're confused, would be to write the equation, and you don't necessarily have to do that, but some people find it really helpful. And so in this case, they gave us 1.200 grams of the compound, and it formed 3.516 grams of carbon dioxide and 1.007 grams of water. And they want the molecular formula, so we'll have to find the empirical formula first. Remember that that's always the case. And then they've given us a molar mass of the compound to compare to. So let's go ahead and get started and see, hopefully you can figure out where you might have gone wrong. So from 3.516 grams of carbon dioxide, I'm going to try to figure out how much carbon was in my initial compound. Remember that that carbon transfers all to the carbon dioxide. So grams of carbon dioxide to grams of carbon, and we're going to use the molar mass for this. So in carbon dioxide, I have one carbon, that would be 12.01 grams, and the total mass of carbon dioxide is 44.01 grams, and that gives me 0.9595 grams of carbon in the compound. From the water that was produced, remember that all of the hydrogen in the compound ended up in the water. So from the water that was produced, we have 1.007 grams of water. And we're looking for elemental hydrogen here, not like the atoms of hydrogen, not hydrogen gas. So this will be grams of H2O to grams of H. Remember, there are 2 or 2.02 grams of H in every 18 grams of water, and those numbers came from the periodic table. This is one place where you might have made a mistake. So this would be 0.1129 grams of hydrogen. And then to find the grams of oxygen, I need my initial mass, which was 1.200 grams of compound minus the 0.9595 grams of carbon, minus the 0.1129 grams of hydrogen, and that gives me 0.1276 grams of oxygen. So now I have grams of all three elements in the compound, carbon, hydrogen, oxygen, and I'm ready to do my empirical formula. So we don't need percent to mass because we have masses. So we will do mass to moles next. So we're going to come in and do mass to moles for all three of these. So grams of carbon, 1 mole of carbon, that would be 12.01 grams. Grams of hydrogen, 1 mole of hydrogen, that's 1.01 grams. Grams of oxygen, 1 mole of oxygen, that's 16 grams. And so now I can do the math. So this would be 0.079891, do not cut them short, moles of carbon, 0.11178. So I had 4 sig figs, so I'm going to keep at least 4. I kept 5 here, moles of hydrogen, and 0.007975 moles of oxygen. And so I did my mass to moles. Now I'm going to divide by small. So the oxygen would be the small, so 0.007975 divided by 0.007975 divided by 0.007975. And what I see after I've divided by small is that I get 10 carbon, and it's pretty close to 10, and I get 14 hydrogen, and it's pretty close to 14, and I get 1 oxygen is exactly 1, right? So the empirical formula already has whole numbers. I didn't need to multiply to whole here, and I'm done with the empirical formula. But they asked me for the molecular formula. So I need to find the empirical formula mass by doing 10 times 12, or 12.01, and 14 times 1.01, and 16 times 1 for the oxygen, and that gives me an empirical formula mass of about 150. It's like 150.24. So now I need to take the 300.42, that's the molecular mass, and divide it by the empirical formula mass. So that's divided by 150.24, which is approximately 2. Or I do it this way, 150.24 times what equals 300.42, and that would also be 2. So now I'm going to show this work. C10H14O times 2 equals C20H28O2, and there's the molecular formula. So if you hopefully you found where your mistake was, you will perhaps be ready to try again. So let's do another one. All right. I would suggest that at this point you stop the video and try it on your own, and then restart again for the answer and the explanation. So copy it into your learning targets, because if you're doing this, you probably were not successful the first time, and we'll go from there. So I'm going to read it, and then you can stop the video. So we have a 0.3629 gram sample of THC, which is the principal active component of marijuana. You're going to discover that college textbooks talk a lot about things that might be relevant to college students. So unfortunately, we are stuck with this. And they burn it and yields 1.0666 grams of carbon dioxide and 0.312 grams of water. What they don't tell you in this question that you need to know that I've added here is that the compound actually also contains oxygen. I discovered this because when I added up my amounts of carbon and hydrogen, they did not add to the 0.3629 grams that the whole compound was. So this is something that the question would not leave out if this were an AP question. So the first thing I'm going to do is start with my grams of carbon dioxide to find the grams of grams of carbon. And this would be where you want to stop the video and try it yourself. Come back when you're finished. Okay, so I'm going to do 1.0666 grams of CO2. And I'm following the same pattern, grams of CO2 to grams of C, 12.01 to 44.01. And that gives me 0.291067 grams of carbon, then 0.3120 grams of water, 18.02 grams of water to 2.02 grams of H. That gives me 0.034974 grams of H. I'm going to do the total, 0.3629 minus the carbon, 0.291067, minus the hydrogen, 0.034974, to find 0.036859 grams of oxygen. And now I'm ready to do empirical formula calculations. So I have masses. I'm going to convert to moles. 12.01 grams of carbon in 1 mole of carbon, 1.01 grams of hydrogen in 1 mole of hydrogen, and 16 grams of oxygen in 1 mole of oxygen. And that gives me, where are we? 0.024235, 0.034628, and 0.002303. And I'm going to divide by small, which would be this one, 0.002303, 0.002303. This gives me 1. This gives me, at the top of carbon, 10.5, and this gives me 15. So because of the 10.5, I need to, it doesn't look like a point, hang on. So because of the 10.5, I need to take that by 2, and that will be 21, and 15 times 2 is 30, and 1 times 2 is 2. So the empirical formula is C21H30O2. Okay, and they did not ask me for a molecular formula. They didn't give me a molecular mass, so I'm done with the empirical formula. Hopefully this was more successful for you. If you need to, you can keep going. There's another example that's very much like this. So again, we have an alcohol, and I give you a hint that alcohols contain carbon, hydrogen, and oxygen. So I'm going to talk a little less and just kind of put it on screen so you can watch what's happening. I'm first going to find the carbon from the carbon dioxide. You can skip ahead if you'd like. I'll tell you the final answer. The empirical formula is C3H8O is the empirical formula. Okay. If you were correct, then you don't need to watch this part. You can skip because there is something different coming at the end. If you need to watch, then you can watch. I'm going to find the hydrogen from the water, so 0.306 grams of water. .02 grams of H gives me 0.0343018 grams of hydrogen. I'm going to take the total, the 0.255, and subtract the carbon and the hydrogen to get 0.067605 grams of oxygen. I'm really not being careful with sig figs, I'm just keeping lots. Then I'm going to divide by small, which is the oh no, I have not. I have moles. I have to go to moles first, sorry. So I have grams of everybody. I'm going to convert to moles. And now I have 0.012747, 0.033962, and 0.00042253, which is the small. So I'm going to divide them all by the small. And 0.004223. And these came out to whole numbers the way they were. So my empirical formula then, this is the carbon, this is the hydrogen, this is the oxygen, would be C3H8O. All right, so hopefully after all this practice, you're getting better at it. I do want to do another example of elemental analysis that's a little bit harder, that's a little bit different, and is going to make you stretch a little bit. So let's try this one, and I'll talk you through it in the beginning, and then you can try it yourself if you want, and come back for the answer and the explanation. So what's happening in this question is that we have 0.8150 grams of a compound. It's MCl2, and so we don't know what that M is, but we know that it must have a charge of 2+ because it has 2 chlorines with it. Okay, 2 chloride ions with it, and it's reacted with excess silver nitrate. So basically we have MCl2 plus silver nitrate, which is AgNO3, and the silver chloride precipitate that forms, which is AgCl, is filtered, rinsed, and allowed to dry. I'm actually gonna finish the equation, although I don't really need it. This would be a double replacement, which would give, sorry, I wrote MgCl2 just out of habit. It is not magnesium. It's hard to write M, okay? So I would get MnO3 twice because we know that M is a charge of 2+. I'm not going to balance the equation because I'm never going to use these coefficients, but I do want you to look that we had 0.8150 grams of MCl2 to start with. We had excess silver nitrate, and we formed 1.8431 grams of silver chloride. They never mention the other compound because it's still dissolved. Okay, so we dry this, we do all this, and now they want to know the identity of metal M. So this is like the other one that was in your topic 5 part 2 lecture, where we need molar mass to identify it, which equals grams of M per moles of M. Okay, so unlike the question that was in your notes, you know neither of these from what you were given in the question. So we need to do 2 separate things to find the grams of M and the moles of M. All right, so we can start wherever you'd like, but notice that what we really know about this is that all of the M that was in this compound ended up over here, and all of the silver that was in this compound ended up, or sorry, all of the Cl that was in this compound, let me change colors here, ended up in the silver, bless me, excuse me, in the silver chloride. So the idea would be that I don't know much about M because I don't know how much MnO3 twice I formed, but I do know how much chlorine, and since I know who chlorine is, I also know its molar mass. So let's see what we can do with this. You try it if you'd like, and then restart the video. All right, so let's look at this. The way that I worked this is I started with the silver chloride that I knew, 1.8431 grams of silver chloride. And remember that I'm trying to find the grams of M and the moles of M. So I'm going to use this to find both, starting here. All right, so I'm going to do 143.35 grams of silver chloride. This is from the periodic table. It is equal to 35.45 grams of chlorine. You might wonder why I'm looking for the chlorine, but that's because if I can figure out how much chlorine was in this 0.815 grams, then I can figure out how much of it is M, and that will tell me the grams of M. Okay, so I'm going to do this, and I discovered that this is 0.45579 grams of Cl. So to find the grams of M, I'm going to use the total, which was MCl2, 0.8150 grams, minus the 0.45579 grams that were the Cl. And that's going to give me 0.35921 grams of M. I'm going to come down here. At the very bottom, I need molar mass of M to be able to identify it as grams of M over moles of M. And I now know the grams of M, 0.35921 grams of M. So I still need to do work to figure out the moles of M, but at least I know half of this. So the moles of M is a little trickier, okay? What I can do is start with my grams of chlorine and then use the chemical formula, but then it has to be in moles, okay? So I'm going to start with a 0.45579 grams of Cl and go from grams of Cl to, moles of Cl. And that's 35.45 from the periodic table. And then moles of Cl to moles of M. And this is going to come from the formula. We know that it's MCl2, so that means that we have 1 M for every 2 moles of Cl. And when I do that, I get 0.006428 moles of M. And that number, so now let's look at what we've done here. This number can come down here, whereas this number of grams came in here. Okay, so now I can put this in 0.006428 moles of M. I'm going to get grams per mole. It comes out to 55.88 grams per mole as the molar mass of M. I'm going to go find a periodic table. Clear this all off so that we can see what we need to see. And I see that iron is 55.845, cobalt is 58, manganese is 54. I think this is iron. So I can come back here and say, I know this is iron. And I've identified the metal as M. And in the compound it would make sense because iron can be iron too. So there we go. So hopefully this extra little bit was helpful. You'll get some opportunity to practice all of this some more, and I hope this helped.